Howdy, everybody. Hope you're having an amazing day, amazing weekend. I guess you may not be watching it on the weekend, but it's a weekend for me. Um, and I just I'd made a post this week about the thing I was going to be working on this weekend. I gave you a couple problems to look at, and we're going to go over those problems today. And I kind of hinted at what we'd be talking about, which is the sliding window algorithm. Um, to solve those problems. But before we get into it, again, I, as always, want to say thank you. I really do appreciate it, right? I don't want you to feel like, oh, every introduction he's saying thank you. But I really do appreciate all your feedback and all your comments. I'm keeping a list of the things you're saying, the things that I can improve on, and like new videos that I can do. And I truly do plan on working on those things as I have time and as I get through my list of things that I want to talk about. So, but as always, keep giving them to me. The things that you share with me are really interesting, and are something really worthwhile for me. And I hope this video and these videos are worthwhile for you. So, with that, let's get into it. So, if you hadn't guessed from the post, what we're talking about today is the sliding window algorithm. Some people call it a technique, um, but what is the idea behind the sliding window algorithm? In general, is it works really well on arrays or series of data. And what it does is what you do is you create like little windows within the array, um, and slide those windows around, right? That's where we get the sliding window from. So maybe your window, oops, I'm using these left and right pointers to denote the start and the end of the window. But so maybe you have some window that's this size, and you're going to start sliding around, and so maybe the right will slide here and then the left will slide here, and then the right will come here, and then the left will go here, and then like at that point you're done, right? It really depends on the algorithm, and we'll go over the details of it. But the general idea of the sliding window algorithm is you're going to create small subsets or windows of that data that you're processing. Again, usually some kind of array or series of data, right? And from that, you can like track what you're doing and come to a solution to the problem, right? This algorithm falls under dynamic programming. So I think we've talked about that a little bit before, but the general idea is, can you break a larger problem into a smaller subset of problems, and then from those smaller subsets derive your solution, come to the answer, right? And so you can think about the sliding window problem as, can I solve can I just solve the problem within here? You right? Can I track some state or do something in here to solve that problem and to come to a solution, right? And and in that sense, it is a dynamic programming thing. And I actually looked. It's strange they don't have a Wikipedia article on it. I may have just not searched very well. I've always heard of it as the sliding window problem, but maybe it's called something else, and that's why I couldn't find it when I was looking for it. Um, but just again, at real general is, can I create little windows of a problem to solve, and can I use those windows to update some kind of state that will eventually get me to the solution? And you might ask, well, why do you do this? You've probably actually used it before and you just don't know. Many times when you're iterating over an array, you're doing some kind of sliding window program. Um, but it allows you to do it with like a single pass, is the way to think about it. Is in many cases your complexity can be O of n, meaning you've just kind of slid through it once. Whereas in many brute force solutions, it would be n squared or n cubed, because you're like iterating over the array and iterating over the array. We'll talk about that more in a minute, but it's mostly an efficiency technique, right? Is to say, oh, if I can think about how to solve this in a window style, sliding window style problem, I can solve it faster than if I tried to, uh, you know, solve it with just the normal brute force. So what do you need to know about solving the sliding window algorithm before we get into the first problem? Um, Obviously, you're going to track some pointers, right? You're going to have a left and a right pointer that you're going to track. And these are just pointers to where you are in the data or in the array that you're working with. We'll work with arrays, but you could do this with like time series data. So the places that I've seen it used in the real world and not just for problems is like IoT data. You're getting a glut of data and you want to do like um, you want to be able to process that data and glean information as it's coming in. You can use something like a sliding window technique to do that, right? So anyway, what you want to know is where is my window? How big is my window? And so that's usually um, uh, tracking it with these left and right pointers, right? So where is the beginning of the window and where is the end of the window? I've always used left and right. I suppose you could use beginning or end, but the idea is where does the window begin and end? So these are the things you want to like do to solve your problem, right? Is define your window. And that's just with these left or right things, right? How do you do that? And then what you want to know is what is your state, right? And we'll talk about this more as I think it'll make more sense as we go into a problem, I think I should say. But what is the state you're tracking, right? So you're going to be doing something with the window and you want to keep track of that with your state. The first problem is like what is the largest sum? So you're going to be tracking your largest value, right? And then you need to kind of figure out how you're going to iterate over it, over the window, right? Is the window a static size? Are you going to just like march down the array, which is what we're going to do with the first problem? Or is it kind of accordion style where the left may squeeze to the right and the right may come out and the left may come in, right? These things, I guess maybe I was doing that off window, but the left and right, as you get into more complex problems, can be more accordion like. And as they're moving, they won't move together, is maybe the way to say it. So you want to decide how you're going to iterate. And then finally, boy, I'm really doing good at those stars, aren't I? You want to know how do you update your state, right? So how am I going to, once I've adjusted my window, how do I like update my state? And sometimes these two kind of happen in the same time. Like you'll be iterating your left pointer as you're updating, and these kind of often happen in tandem. But these are kind of the four things that you want to be interested in when you're trying to solve a sliding window algorithm. How do I define my window? What does it look like? What state am I interested in tracking? How do I iterate through the window? How are my left and right pointers going to update? And then how do I update my state, right? How do I track that information that's changing, right? And I think the best way to do this is let's just start with one of the problems. This one isn't a LeetCode problem. I thought I would share it though, just so you could kind of get an idea of uh, how the sliding window problem works. So the question is, given a list of numbers and a number k, return the largest sum of k consecutive numbers in the list. Okay, so that may be a little hard to parse because especially in LeetCode, they use k or these type of things a lot, largest sum, and they just assume you know what they mean, right? But the idea is you're going to be given a list of numbers and you're going to be given some size k. That's going to be your window size in this case, and they want you to find the largest window, the largest sum of that window when it comes up, right? So if you imagine k is 3, um, right, and well, you can actually do this in your head, right? If you kind of look, what is like the three largest continuous values? It's 3, 4, and 5 in this example, right? So um, uh, it would be right here, right? These are the three largest that are consecutive to each other, right? And so you could visualize with this, but how would you do that algorithmically, right? Well, first we define our window again, and in this case, Because we know that we're just looking for the largest of size k, it specifically says it's of size k, right? So we know the window is that size. So if we're given a k equals 3, it's always going to be 3. So we know that our left and right are going to slide together, right? So now we need to determine what state are we going to track. Well, we want to know what the largest one is. So, oops, that was a terrible A. So the largest is what we want to track, right? That's going to be the largest sum that we get. And then how do we iterate through this list? Well, because k is static, right? It's always going to be of size 3. We can just like march both left and right together down the thing, right? And then how do we update? Well, as we're moving, we can just track the sums. And if we ever find a largest, we can create that largest value. Or we can, sorry, we can update our largest value, I guess is what I should say. So let's actually just try that. We know our window is 3, so we're going to start here with our left and here with our right. That's 3, right? And then we want to just iterate through them, right? Well, what is our current largest? It's 6, so we're going to update our state. And then we just need to keep iterating. We're going to move left here and right here. And then we want to count this one again, right? And if my math hasn't failed me, that's 9. And then we want to iterate again, right? So we're going to move 3 here and 5 here. And now this new value is 12, right? And now we've reached the end of the array, so we know we can't go any further, and so we're done. We know the biggest is 12, right? Let's do this same thing, though, but with another problem, right? Let's say that we'll still call k3, but let's put a negative value in there, right? So we're still going to do k equals 3, and we're going to track the same state, but I'm going to show you why. We're just like kind of give you a reason, show you why this works, right? So here we go. We're going to start. We're always going to have a size 3, like I had mentioned before. We're always going to march down together. We're going to keep the size of the window is going to remain the same. And then we're going to track our largest. So what is our current largest? Is 6 here, right? So notice the numbers are the same, but I put a -4 here. You can probably guess what's going to happen, right? But here we're going to move down, and now what is our sum? Is 5 minus 4 is 1. Oh, that's not bigger than the largest, so we don't need to update our largest, but we're going to now move our state down. And now we're going to track this, which is 3 minus 4 plus 5 is 4. Is that right? Yeah. But that doesn't change our largest value. We already had 6, so we now know our largest is 6, right? Pretty simple problem. But you can see how, as we know we have to go. Excuse me. We know we have to go through the array, so we can just kind of track going up and down the list and doing these things we've talked about, right? What is our window size? We know it's always going to be a K3 or whatever they give us, right? What is our state? We're tracking the largest. How are we iterating? Again, we're just going to kind of march down. And then how are we going to update? Well, if we ever find one that's the largest, we want to use that value, right? We're going to use that value. Okay, so we've kind of talked about this, thinking about it in my mind. How does it work in code? Yours might look different if you did it in another language, but here's a potential solution in Rust, right? I've tried to highlight the things that we need to be interested in. So first, we're interested in our state. And again, we want to know what our largest value is. So we're going to put that's the state that we're interested in. I've just set it to the minimum size for now. You could use other things like, the idea was, because it's an integer value, it could be a negative number. So we wanted to start at the minimum. Anyway, but how are we going to slide? Remember, we're always going to slide k values, or we're going to have a window of k and it's not going to move and we're just going to march down. You can actually do this with an iter, or with a range and enumerate. So you can see I have my left and right value. Well, my left is the enumerate, right? It's going to be 0, 1, 2, 3, 4, 5, and so on. And my right is starting from K to num lanes, right? Num's lane, right? So I'm starting at K, so I'm starting at 3, and I'm going to the end of the array is the way to think about it. And so this is just kind of fancy shorthand to say, hey, here's a way, if the size is static, that I can just march down it, right? My left will start at 0, my right will start at K, and then they'll just both slowly increment up until you reach the end of it, right? So this is how I'm going to iterate my left and right values. Okay, and then the next question is, how do we update our state, right? So, well, this one's pretty easy. Again, we're just tracking sums. So I just take a slice of the array from left to right, and I sum them up, and then I update my largest, right? I take the maximum of my current largest with my new sum. So whichever one's the largest, I'm going to set largest to. And then and that's it for this algorithm, right? So I have my state, I'm going to slide through it, I'm going to find the largest value, and then I'm going to keep track of that largest value, and then when I'm done, I can return it. Okay, there I did it this way, I should say, just so it's clear that what we're doing is we have some state, we're going to iterate and update that state, we're going to mutate it, and eventually that will give us our value. There's ways that you could potentially do this faster. If you were tracking like your current sum, for example, as you're removing values and adding values, you could slowly you could like just update the state. Like, imagine, maybe the way to imagine it is, say you're like right here and right here, and your current sum is 9. Well, as you're moving things over, you're going to subtract 2, which would give you to 7. You're removing this part of your window, and then you're adding this part of the window, which is 5, and 7 plus 5 is 12, right? So that's a potential shortcut if you're looking to like maximize speed, is you could just be tracking what's your current window size, and as you remove parts of the window from the left side, you subtract it from your current size, and then as you're adding from your right side, you add those values and get to it, right? So that's a potential way to like improve the performance here, but I think this helps just kind of illustrate of what we're doing, right? We're going to have some state we're going to track, we're going to iterate through it, and then we're going to update our state. Okay, so let's use this to solve some LeetCode problems, right? I kind of don't want to show you the answer over here because I want to talk about it, but let's read the problem and see how you might go about solving this, right? So that first one was an easy one. We're going to do a quote unquote medium, but I promise, if you think about it in the sliding window algorithm, it doesn't get much harder, okay? Just as you're reading this, think about, what is my state going to be? How am I going to iterate? And how am I going to update that state, okay? Says, given a string s and an integer k, return the length of the longest substring of s that contains at most k distinct characters. Okay, this sounds a little confusing. So it might help to think about this for a little bit, right? You're going to be given a string s, and you want to return the length of the substring that contains the most k distinct characters. So let's assume k is 2 in this example input. What is that asking you? So when it means distinct characters, it means if you've already seen that character, it doesn't go towards your like total character count, if that makes sense, right? So you can see this one outputs 3, and that's because E, C, and E contain 2 distinct characters, the letters E and C, right? But that's the only place that's the largest one, right? Consider like these 3, that's 3 distinct characters. That doesn't work. Here's 2 distinct characters, but that's only 2. Again, this is also 2 distinct characters, but you could take it even further and go right here, right? So you could do these 3 to get you that value. Maybe I'll zoom in a little bit so you can see it, right? Again, so maybe the way to think about it, and we can start looking at like what it would look like is we have something like this. If our value was 2, if our k value was 2, we could actually use like this whole block right here, right? Because it only contains the letters A and R, right? And so even it's 4, the answer is 4, but we only use k distinct characters because they'd only used A and R. So let's think about what kind of state we want to track, right? Because it's distinct characters, um, uh, maybe the way to think about that is I probably just want to know how many unique or distinct characters I currently have in my window, and then ask yourself what's one way to do that, or how would you do that? I noticed in one of the solutions, I think it was Gordon 508, they actually created a counter um, data structure, and that works really well because it's meant at least the one that I've seen in Python. The idea is you insert values into like the counter data structure, and it keeps track of how many times you've seen that specific value, right? And that's a good way to do it, right? Is like as you add or remove items, you can figure out, hey, how many distinct values do I have in my quote unquote counter? Um, Maybe we can just look at it in code really quick. Yeah, here's their counter thing, right? So the idea is as you're adding values to the counter, it's keeping track of how many there are of those values, right? So I won't go into too many of those ways. The way that I solved it, though, and I think maybe it will make more, maybe how do I say this? Maybe is like the easiest way to start thinking about it. If you're not familiar with it, using a counter is just a map, right? So if you think about if you have some kind of map that just says, "Oh, how many A's do I have? I have 3 A's, and how many R's do I have? I have 1 R. What is my set right here? Well, I only have 2. Okay, so I can keep going." So a counter is essentially this. Essentially, the way to think about a counter is it is a hash map, but it's just a hash map with like some special properties that make it easy to add and remove values from the list. Um, so either way works. It's just we need to some way to track how many integer or how many values do I have in my solution or in my window, and what does it look like when I add or remove them, if that makes sense. So that's going to be our state for this one. So we'll say our state is a map or a counter, right? However you did it. If you look at my code, I essentially created a counter. We'll look at it in a second. But we're going to have some map where we're going to track how many distinct characters do I have, right? So what is the next thing we want to do? We want to know how we're going to iterate over it. Well, remember we're trying to like maximize the length, right? So the question it asks is what is the longest substring? So our goal is actually to increase the window as much as we can and keep track of what the largest one is, right? So I should actually add that to our state, right? What is the largest window we've seen so far? That's another state that we want to track, right? Again, I apologize for my writing. What that means is our left and right values are going to be independent, right? So we're going to try and move right as far as we can until we break the state, and then we'll move left to get us back into the state. So that's how we're going to uh, uh, iterate through it. Again, we want to max right and then fix with left is the way to think about it, right? We're going to keep moving right as far as we can until we've like broken the constraint, which is at most k distinct characters. So we're going to keep moving right as long as we have a valid map of distinct characters, and then we'll move left to fix it, to get us back into the right state, if that makes sense, right? Um, and then how do we update is the last question, right? So how do we update this? Well, obviously we just need to update the map with um, our with new and removed values. Boy, I probably should like create slideshows, right, or presentations for this, right? But this is I kind of like to do it this way, but because I feel like I'm like a quote unquote teacher on a chalkboard, I guess. I don't know. Anyway, the idea is, what are we going to do? Is, well, we'll just update our map with the values and um, track our we just update our map, and that will infer what we need to do next, right? So let's actually just run through this problem once. Our map's going to change a lot, so I'm going to keep track of it over here, right? Um, and we'll keep it in a map, so we'll have counts. And so I'll try and do that, right? So we're gonna start with we're gonna start obviously at this position, which means we're going to add a to our map. So we'll say a equals 1. And then our largest is 1, right? So that's the largest we've gotten so far. That's our like initial state. And how are we going to iterate? Well, we're going to keep maximizing right until we break it, right? So let's move right to here. So that gives us an R in here, right? So now R equals 1. We still have, what is our K? Our K is 2, right? So we still are right here, AR equals 1. And our largest now though is 2, right? So we'll update that. We've now found a new larger one. Okay, so let's keep moving right. We move right here. We now have a equals 2. And now our largest is now 3, right? So we found a new largest of 3. And we haven't broken it. We still have 2 distinct characters, so we're still good to keep iterating, right? So now let's move it again. We have another A, so now we're 3, and now our largest is 4. So we'll update our largest to 4. And we still haven't broken it. We still have 2 distinct characters, so we know we're good. And so let's keep iterating. So we're going to add a C. And so now we have a C equal to 1. And at this point we say, oh, we've now broken the constraint, right? Our K is 2, we have 3. So now we need to slide left and start removing values until we get back into a good state, right? So let's go through that process. We're going to start moving left, so we're going to move left here, which means we need to remove an A. So now A is going to be equal to 2, right? But it's still broken. We still have 3 right here, so we're not done. So we're going to move left again to here, and that's going to get rid of an R, right? So we're going to remove this R from the list. So now we actually are in a good state. Our window size is 3, and we have 2 values, 1 C and 2 A's, or 2 distinct values, right? But that's not larger than our largest, so we aren't going to update our largest. But but now we can keep moving, right? So we'll move our right to right here, and that has an I in it, right? So we'll add an I to it, and that will give us a 1. Oh, it's broken. So now we need to move, right? So we'll move this, and that will give us 1A now. We got to move it again. We're still in a bad state. We remove our last A, so now our A is gone, and now we are in a good state. But you can see our largest window size hasn't changed, and we've now reached the end, right? So we know we're done. We could potentially move, I think in the algorithm, we would still technically move this to right here. Actually, I don't think we do because we're done, right? But this will then remove this value right here, but it hasn't updated our largest at all. So we've now slid through the array, and we now know our largest is 4. That's our answer to the problem, right? So this was a little bit more complex, But again, think about what we were doing. It wasn't that crazy of an idea, right? Is we said, "Oh, this looks like a sliding window problem. What do I need to track? What is my state?" Right? We're going to track that map or counter. We're going to track our largest value. And then how am I going to iterate it? Well, I want to maximize the window. So I'm going to try and go right as much as I can until I break it. And then I'm going to go left until I'm back into a good state. And I'm just going to do that over and over again, updating my map values until I've gone through the whole array. And that is the sliding window algorithm at its like purest form, right? Is what is the state? How do I iterate? And how do I update that state? And you've taken a problem that if you tried to solve this in brute force was really hard, right? Like if you think about the brute force solution is you're just literally trying every combination of like size throughout the whole array, right? And and instead you're doing it in O n of time now. You're just going through the array once with two pointers that is getting you to your solution. Okay, so how does this look in code? Let's go look at it right here. I have a lot of comments here, but you can actually see there's not much to it, right? And that's the beauty, I think, of these algorithms is once you understand them, the technique is actually not that hard, right? So in LeetCode, they give it to you as a string. We're going to turn it into a vec of characters. I think someone had asked the question about this is how do you deal with strings and characters? Um, because we're only using ASCII, you could potentially turn this into an array of bytes and just work on bytes. But for me, I just collect it into a bunch of characters, and then I can do that. I can do a whole video though on characters versus bytes and stuff like that. Maybe I'll just say though, in the old C days, before we were doing everything in Unicode, you literally just got a character. It was an ASCII byte, 8 bytes, and you could do whatever you wanted with it though, right? Eventually, you got into like wide characters, is what they called them in C, and that's more akin to what we are doing in UTF-8, right? What I would say is if you know you're working in ASCII, it's not terrible to use bytes, right? You could literally just turn this into give me the bytes of this thing, or you could say as bytes. This is another method, and it'll give you the array of the bytes and treat them as bytes, I guess is the way to say it. And those are traditional ASCII characters in C land. But just for the sake of, we're all trying to use Unicode and being Unicode people, um, you can just use cars, the thing here. And what does it do? It does the work of figuring out where the actual or character boundaries are, right? For you, and then you don't have to worry about it. So I think I'm because the question came up, I'll talk about this much more in more detail. But again, just at really a high level, I usually just use cars. If you're going for speed, like in my previous video, and it's ASCII, sometimes treating it as bytes is going to give you better performance because you don't have to do the word boundary checking and stuff like that. But for this problem, I think we'll just say, hey, we're going to just use a vector of characters so that we can go through the characters, right? And this is what I have to do in Rust to do that, right? Is they're going to give me a string. I'm going to turn it into a vector of characters so that I can have kind of pointers into that vector and move through it. And that kind of will help you solve the problem in that respect, right? Okay, so given that, now we have a list of characters. What is our state for this problem, right? Well, like I said, you want some kind of counter, and so I did a hash map. But yeah, I thought it was cool that Gordon 508 implemented their own counter, which was akin to this right here in Python. This is a cool thing. I think it's actually really useful, especially for a sliding window style algorithm. So it was cool to see them implement that, and that works just as well. Um, what it will do is you'll get fewer of these weird things that look kind of funny in the algorithm because the counter thing does all that stuff for you on the inside or internally. We also want our longest value, right? So what's our longest substring that we found for the problem, right? So those are the two states that we want to track. And then the question is, how do we iterate? Well, remember, we want to maximize right and then slide left until we, after we've broken it, broken the constraints. And so we're actually going to track them separately, right? Right will always slowly be marching forward one by one through the list. But left is going to try and stay in its position as long as it can. So we're going to track that separately, right? And then what do we do? How do we update our state? Well, the simplest way is just to add it to our map, right? And so this is the Rust way of doing that. Again, we get the entry for our character or its default value, which is 0, and then add 1 to it, right? So this is just saying, hey, increment we've seen this character incremented in our map, so we know that we've now, like, quote unquote, seen that character is the way to think about it. And then again, we're trying to maximize the right. So we just need to check until we've broken the constraint, right? So we just need to check when have we broken the constraint, and that's with this while loop. So we say while the length of our counts, this is like how many elements are in the hash map, or how many keys are in the hash map, right, is greater than k. So if we ever go over k, now we need to shrink, right? So if we're ever under k, we know we're done. We don't have to worry about this, right? That happened quite a bit at the beginning right here when we had left and right over here, is we were just slowly marching right over, I think, to right here was the largest point. We can just keep doing that, and we kept doing that until we got to C, and then our map was larger than we wanted to, right? So as long as we're still within our bounds of the question, all we do is we just say, well, we just update our largest, right? Or our longest in this case, I think I named it, where we say, what is the maximum value of our current longest and our right minus left plus 1, right? What is the length of this array of values, right? So it's another one of those off by 1 things, right? Is because these values are inclusive, we want to add 1 to it to get there. Okay. But what happens then when we've gone over, right? Now we're at C, and now we have 3 of these. Well, at this point, now we want to move left until we are back in a good state, is the way to think about it. And how do we do that with a map? Well, we find what our left character is, and then we remove that character from our thing and increment left, right? So we're moving left 1 position forward, and we want to remove it from our map, right? So in our first instance, when we moved this over here, we got rid of one of the A's, right? So we did I say increment? It's decrement. We decremented it. We reduced it by 1. There's one key thing we want to do with a map, though, right? Is this will just it's happy to accept negative numbers, or, well, I guess it won't, because I think I used a U size, and so you'd get a stack trace. But we want to check and see, is that left value now 0? And if it is, we remove it from the list, right? And you saw that was me doing the squiggly lines down here, right? So if we ever get to a point where we've removed all of the A's, we can just remove A from the map completely, and that will allow us to get back. That will update our counts len so that we eventually get back to K, right? And that's it. That's the algorithm right there, right? So again, we're tracking state, right? We want our counts and we want our longest value. We're going to track those 2 values. How are we going to iterate here? We're going to try and keep going right, and so we're going to keep left where it is and keep moving right until we've gone too far. And how does that look? Well, we're obviously going to increment our count of our character count, our map. And then once we've gotten to a point where we have too many values in our map, we're going to slide left, and that's what like this part, or sorry, this part is right here. We're going to slide left, removing it from our map until we've like removed enough values such that we're back into a good state, right? And we're just going to slowly do that over and over again. Okay, so again, if you look at it, there's actually not much code to it, right? And when you break it up into those three things, hopefully it makes more sense, right? You just have to be willing to ask yourself, the problem is, first of all, is it a sliding window problem? And then second of all, what is my state? How am I going to iterate? And how am I going to update it? Okay. One last problem, and this one's listed under hard. But again, I think if you like look at the problem and once you understand it, it doesn't actually become that hard because you're not doing much more different than you're doing with all the other problems, right? You're going to say, what is my state? How do I iterate? And how do I update, right? So let's look at this last one, and then we'll be done. Given two strings s and t of lengths m and n, respectively, return the minimum window substring of s such that every character in t, including duplicates, is included in the window. If there is no such substring, return the empty string. The test cases will be generated such that the answer is unique. This is just a thing of like, it's possible that what they're saying is they won't ever give you a case where it's possible to get multiple answers of the same size, right? Maybe the minimum, you can find two minimum windows of the same size that do it. They're saying they won't do that for you. So, but obviously they have window in the word, so that should give you a hint that it's a sliding window. But I want you to think about like what this is saying, because it can be kind of hard to parse at first, right? They're going to give you two strings, and they want you to find the minimum substring in S that has all of the characters in T, right? And they give you a more complex example, or kind of a big S right here and a relatively small t. But think about what it's saying is, right? They're going to give you ABC, and you want to go through here and find out what's the minimum window that contains all of the characters A, B, and C. And notice they say including duplicates, right? So you could potentially get an AA, and you'd want to have two A's in that substring, right? So as you're looking at this problem, right, obviously you can see like this substring contains A, B, C, right? There's an A, B, and a C. They don't have to be in order, right? It's just that they contain those characters. But that one is 1, 2, 3, 4, 5, 6, right? And you could even potentially say, oh, this one contains it too, but that's even bigger than 6. They want you to find the minimum. And visually scanning, if you take a second, you can actually see that it's right here, right? This contains the letters B, A, B, and C, and it's only 4. And if you kind of go through this, you can see like right here, you could technically get it, but it's much larger than 4, which is this value right here, right? So hopefully that makes sense of what the problem is. Now the question is, how do we do a sliding window subproblem, right? How do we do this sliding window problem to solve this thing? Again, I want you to think about what is your state. What is your state? If I can type or write directly. How are you going to iterate? And then how are you going to update? And like I've said, these two often kind of fall in the same categories, but these are the things I want you to be thinking about as you're going to do it. Well, what do we want our state to be? Obviously, we want to know what the smallest is, right? We're trying to return the smallest. And we also want to kind of, maybe the way to think about it is we are interested in what characters we have in the window, but we're more interested in how many of the characters of T have we seen, right? So we want to keep we want to track the characters of T that we've seen. And then how will we iterate? Well, again, we want to do the smallest, right? So our iteration will be to move right and then move left as long as we are, as long as we have all of t. Again, I apologize. So there's our thing. And then how are we going to update? Well, we want to, you know, add and remove values in t, right? That's kind of what we're interested in right here, right? Is we're going to have some, we know if our t is, what did we say it was? A, B, C. We kind of are interested in, have we seen all of these values, right? And again, the way I'm going to do this is a map, because you could get multiple A, B's, and C's, but we're just going to like increment and decrement how many of these we've seen. And eventually we'll get to a point where we've seen them all, and now we've found a good solution, and we found our minimum, and we're just going to keep moving them as long as we can. So let's think about, again, or let's walk through it, I guess I should say, with this idea of here's our state, here's how we're going to iterate, and here's how we're going to update, right? Um, and so let's just start that, right? So we start at A, and so here we'll create our little map over here of A, B, and C, and kind of keep our counts. We know we need one A, one B, and one C. And so we're going to keep growing as long as we're valid, as long as we're invalid, and then we'll start shrinking once we've reached our valid to see how far we could get, right? That's kind of our iterate that I talked about. We're going to move right and then move left as long as we have all of t. That's how we're going to iterate through this, right? So let's just start that. We see A, so now we know A has 0, and we aren't in a valid state, right? We're still missing some of these. We want all of these to be 0 or less. That means we've definitely seen that as many times as we needed to, right? So we're going to move this right. D's not in our list, so that actually doesn't help us. O's not in our list, that doesn't help us. B is in our list, so that does help us. So we're going to get rid of the B, and that'll get us a 0, right? We're still not in a valid state, though, so we know we have to keep growing until we found that valid state. E is not in our list. B is in our list, so that moves us to -1, right? So as long as these are less than 1, we know that we have seen all of the values we need, so that's okay. Okay, let's see. We keep moving. Da-da-da. We found an A, so we can decrement A. So now A is -1, but this darn C is really causing problems, right? Um, and N is not in our set of T, so we're not interested in it. We're going to keep moving. Oh, we've seen a C. So now we've seen a C, and now we're at 0. And now all of these are below that value. So we can start shrinking until we break this thing, right? But we now know our current smallest happens to be the size of the whole string, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can say, oh, our smallest is 9. And then we'll just start shifting things off, right? Okay, we get rid of an A. So now A is at 0. And then we keep moving. Not in our list, so we don't care. Not in our list, so we don't care. That is in our list. So B, we want to move that B. It's a 0. We're still valid, though, so we can keep moving, right? E, not in our list, we don't care. B, it is in our list, so we do care, right? So if we were to move this, I should be saying, I should have been updating these values, right? So as of right here, we were at 5, or sorry, we're at 4 now, right? We've moved all of these off, and we've gone from, I should have been updating these. So 9, 8, 7, 6, 5, 4. We're now at 4. If we remove the B, it will make it a 1. So that is not going to be valid, so we can't do that. And so we know that this is as far as we can go, and we're done with the algorithm. So the answer is 4. Okay. This was a bit of a weird one just because the C was at the end, But hopefully you get an idea of what you're doing is you're growing the thing until you've met your constraint, and then you're trying to move the left as long as you can continually hold that constraint. This is where I kind of wanted to show you these three problems because they illustrate really well how you might use the sliding window algorithm. So when the size is static, you're just going to march down the list. When you're trying to find the longest, you're going to try and grow right as long as you can until you break it, and then move left until you fixed it. When you're trying to find the smallest, you're going to move right until you've met your constraint, and then try and move left until you break it, right? They're both kind of the same thing if you think about it like a more general level. But the largest is growing it as long as you can, and then moving this until before you break it. And then the other one is, how far can I get this until I've broken it, and then move it this way, right? So they both kind of are the same side of or a different side of the same coin. Um, but these are all ways to think about how am I going to iterate through it. And hopefully this one gives you a good idea of what that looks like. So what does this solution look like? Let's go to it. Again, there's not much more to it. Most of this is comments and not code if you look at it. Again, we're going to track our characters as in an array, and this is just to simplify the algorithm. If you want to do this as bytes or whatever, you could do that as well. So when I was doing the LeetCode solution, it presented me with some of these weird cases where S or T or both were empty. And in that case, you return the empty string. Obviously, you won't find it in there, right? So I had to handle that case. But for this problem, let's not worry about that. And let's think about what our state is, right? Again, we were thinking about we want to track all the values in T that we've seen, right? And so I'm just going to create a counts hash map that's going to do that, right? So for each value in T, I'm going to increment my count of that character, and I'm going to keep that as my counts list, right? And until all of those are 0 or less, I know I haven't found a valid solution. And then obviously I want to track my minimum window. I think I was just returning a number here, but they actually want you to return the value, right? So I'm going to keep that as a string to iterate over it. And then how do we iterate? Well, remember, left and right will slide independently, so we can just use right as our for loop, and then left will be its own little value that will slowly update as we move around, right? And then here's the algorithm, right? Obviously, when we get a character, if it's in C, we want to decrement it, right? Otherwise, it's not of any value. I think you saw that in the algorithm. The only things that are interesting for this one are actually the ones that are in T. So we say, hey, is there one in T? And if there is, we want to decrement that value, right? And then we want to slide left as long as we have a valid window, right? So what is that saying is where all of the values in my counts array are less than or equal to 0. And we kind of did this work over here, right? Is once we got to the point where they were all 0, we knew we had a valid solution, and then we could keep sliding left until we broke it, right? So how do we slide left? Well, first we want to update our minimum window, and then we want to slide left, right? So what does that minimum window look like? Well, we're just say, hey, if our right minus left plus 1, again, the off by 1 thing, is our window size less than our current minimum window size, or is our minimum window size empty? This is just an extra check because we're using a string right here. And if it is, right, if we found a smaller one is the way to think about it. We're asking here, have we found a smaller one? And if we have, that's our new minimum window. Then we just need to go about updating our map, right? So if we have removed a value that was in T, we want to increment it, right? So that's this part right here. So if left is in our count, we want to increment it now because we've removed it. And so we need to find one of those other values. And this is where the negative number helps. It didn't really show it in this case because it wasn't long enough. But the idea was if you've seen I mean, you can kind of see it here. Actually, it does kind of showcase it, right? When we get here, we are removing a b, but we have another b down the list. And so that b was a negative number. So we know we can keep going until we get to this one, and then it doesn't work, right? So that's just what this is doing is we're going to increment those numbers as we find them. And as long as they're all still less than or equal to 0, we're good, right? And once we've gone through now the whole list, we can just return whatever the minimum one we found was, right? Again, I probably said this 100 times and you're tired of me saying it. I'm sorry. But what is the idea with this sliding window algorithm? Figure out what state you want to track. Figure out how you want to iterate through that state. You know, are you trying to maximize right or minimize left, right? Um, or maybe it's the way to say it is which one are you trying to maximize, right? How are you going to move through it? And then how are you going to update your state, right? And the update and the iterate often kind of, like I said, work in tandem. So you can see you're kind of doing this at the same time. We're updating state here, we're updating state right here, and that's happening as we're kind of moving the windows back and forth. Um, but again, this dynamic programming is super helpful for solving these type of problems. It's the same thing. I don't know if I said this, but actually in work this week, I was able to say like, oh, we can solve that problem with a DFS, a depth first search, doing the tree stuff, right? Like we've been working on before. And my coworkers were amazed that in like 10 lines of code, you could solve a seemingly complex problem, right? That's really what these algorithms are meant to teach you and to help you to do, right? Is if you just focus on the algorithm and here's how the algorithm works, it will do surprising and amazing things in just a little bit of code, right? I have a lot of comments here, but again, think about what I'm doing. I'm really just updating or tracking my state. I'm iterating through the list and I'm updating that state. And so your job when you're solving those problems is just figuring out what those three things are. What state am I going to track? How am I going to iterate over it? And how am I going to update it? So feel free to go to LeetCode or anywhere else, and you can actually do this. Again, I'm sorry I gave you a premium one, but you can actually search for the tag sliding window, not sloting window, right here, and it will give you all of the sliding window problems. You can see I've solved several of them, but all of these problems follow the same thing, right? You can look at this and you can say, oh, they want to give me a median. They're asking for the median value. How do I what is my state, right? How am I going to track these median values? And then how am I going to iterate through the list? And this one, it looks like the window is of size k, which means you always know how big the window is, right? So it sounds like it's probably going to be static. And then the question is, how do I update my state based on where that is, right? And this one looks like it's just a little bit of math and kind of tracking where the quote unquote middle is. But that'll give you an idea. That again, you can solve this quote unquote hard problem just by thinking about what is my state, how do I iterate, and then how do I update my state through that during that iteration process, right? I know it seems crazy, but you can do it. Just think about those things. Again, break down the problem, use that dynamic programming tool set to help solve those problems. Okay, I hope you guys really enjoyed this. Again, I'm going to post my code to a gist that will be in the link. You'll be able to see other people's solutions. I posted the gist early, so you can see theirs. I'd love to see yours too. I looked at all of them. Gordon 508's was great. I think they definitely understood the sliding window thing. The guy in the GIF probably gave it away, right? But hopefully you get an idea of how it works and you can use this to your own benefit to go solve some more problems, right? Some LeetCode problems and get you going on, your path of puzzle awesomeness, right? I love solving these puzzles. It's very fun because it helps me discover cool things or better understand how to utilize algorithms and techniques. And hopefully, it's done the same for you. And so go out there and give this sliding window problem a try. I don't know that I've ever seen one in Advent to Code that was like this, but it's definitely a tool that you can use. Again, like I've said, I've seen people doing this in like with IoT devices. I did some research in the IoT medical industry, and there were a lot of cases where tracking things like averages and means and highs and lows during a given period, because you're getting so much data, using a sliding window algorithm like this was actually really helpful. So uh, there you go. I hope you all have an amazing day. Keep puzzling, keep having fun, keep learning. And again, let me know if there's anything else you want me to talk about or go over. I'm keeping track of all the things you want to that you've mentioned, and we'll do all those things, and hopefully we can keep having fun together. We'll talk to you later.